this is here Egsgard. I hope my pronunciation is all right. He's the president of SurfAnywhere and responsible for a surf wave like Bend. And you actually write in Canada, that's right.
Our project, we're doing the design on it. We're consulting on the recreational design. And some of the concepts that we're talking about today are being used here. This is in the large scale modeling. So you can see in the picture below, that is the state of the model right now. They're doing sediment movement in this gigantic warehouse. So we're really excited about that. We've been advocating for that one for about 10 years, and we got the city to buy in and put in $1 million. Eventually it's going to be 10 to 15 if the whole project goes ahead. The other big project that we've got going on is building a adjustable wave in our river out in the Kananaskis. That one flows at around 30 CMS and peaks around 70. The 1 in 100 year on that one is about 300 CMS. And this is where we're trying to put in quite a complicated adjustable wave system to make a whole bunch of different wave shapes, from straight waves to diagonal waves. We also did a 1.5 years of research a couple of years ago on how to make really good kayak waves, really good surf waves in the same area, and all that information is published online. So that's a bit of background on what SurfAnywhere does. So what I'm talking about now are waves at abrupt drops and how to control the tailwater and keep it low risk, even when you have changing conditions like was just mentioned. So most of the waves are built on this principle. We'll go through it pretty quickly. The one in the top is Salida. This was newly built in Colorado in the United States, and the wave is excellent. It has no moving components, so it's just a concrete structure. Cost them a few $100,000 US, but it was built on top of an existing wave. I really like that wave because it's really, really simple. But there were some issues with the tailwater that I'll talk about at the end. And then below, we have the Hydro Stadium's wave with the ANSI group, which is also an excellent location. So just a couple of examples of how the waves are working. I imagine everyone here may already know this, but there's been tons of research on hydraulic jumps, and this is from a paper by Helga Fuchs in 2017. And this is the basic idea. You get to a drop, water goes up, goes down, you have the recirculation underneath, and you have a recirculation zone above on top of it. So the key design components for making a wave, sorry, hold on a second. Also got some notes on the side too. All right, the first one is having, it doesn't have a number here, but it's having everything being smooth. You want the bottom, the river bottom, you want the walls, you want everything to be smooth, allows the water to go the way you want, keep it laminar, keep it minimize the turbulence. The second part is are these ramps. This is accelerating the water from the high point to the low point. The next part is the horizontal transition, which is 3. This part is quite important. This is a key part for preventing formation of retentive hydraulics, and this is one of the ideas that we're talking about, is how to move these things effectively. This is redirecting the water to be horizontal. If you don't have this horizontal component, then you end up creating a recirculating weir, which people don't like because they can drown you. The next part is the channel walls. We did quite a bit of research on this in our when we did our research project. This is preventing the tailwater from encroaching on the wave. If you don't have the channel walls, then the tailwater floods in from the side and causes the wave to break. If you have good walls, then you are able to make a taller wave. One of the challenges that comes with those walls is it limits accessibility to kayakers. So if you only have one spot where you can build a wave, then it's really worthwhile both for the usage in the community and to get support from people who are gonna help fund it, to allow these walls to be taken down so that you can have kayakers coming in. The next part is the vertical transition. This is the drop off right after the wave. It provides both for safety, and it also allows for that recirculation we saw in the previous image. A couple of pieces that aren't shown on here are in areas with larger flows, you need scour protection underneath the wave. So there is quite a bit of scour. That's when the movement of the water eats the riverbed and takes it away. That happens underneath the wave. And you need to have, it can be large boulders, they're called riprap over here, that you can put on the bottom. You could use concrete, but something to stop the riverbed from being eaten away by the river, which then can make your structure unsafe. And the last part is a way of controlling the tailwater. So the tailwater, you can have a structure downstream of the wave where you can raise and lower the water level. You could use something like the Dream Wave. It's a beautiful system, able to move the entire structure up and down. So you're able to set the tailwater level with respect to the structure that way. And you could do some other adjustments on the structure that we'll get into. So this is the one on the left is from Dawn Surf. This is in Russia, and the one on the right is from Munich, Flosslande. So same sort of idea. They all have those same pieces: smooth channels, ramp. They have a transition. They've got walls on the side, deep drop. All the standard components for making a wave. So what's a retentive hydraulic? You've probably all seen these. They typically happen at dams, and this is when you have a structure that's creating a drop. The water goes down. The horizontal transition is too low, or is low enough that the recirculation forms, and as a result, if you go in here, you get sucked around and around and around and around, and eventually you drown. And you do get let out eventually, or hopefully. One of the dangers with river waves is that when you have big changes in water level, if you use a static structure, you can go from, when the water levels change, you can go from a beautiful wave that's great to surf to a retentive hydraulic that will kill people, or even if it doesn't kill people, it can look scary, and that's not something you want. So you put all this effort into the wave, and you end up with a feature that looks really dangerous to use, and that causes questions to the safety of river waves, and was it worth spending money on this project? Should we build more of them? So how does this form? What does it look like? Excuse me. This is what happens with tailwater when it increases. These videos are from an excellent video by Dominic Pukert, and it shows how when you have low levels of tailwater, you don't really get a wave. You get the maximum tailwater. You raise the tailwater up, you get this beautiful max wave, and then as you go higher, the wave breaks down, and you don't have a usable wave anymore. Additionally, this is from the images from our research. As this tailwater goes higher and higher, once you get a certain point above this horizontal transition, if you have a static ramp, then you get a recirculating hydraulic. So it goes from being a surfable wave to something that is very dangerous or looks very dangerous. So how do you, what can you do to prevent that from happening? So there are a few things that you can do. The first one is if you can control the tailwater elevation itself. So if you can move the tailwater up and down, maybe you have another structure downstream which you can flatten to let more water out, or raise it up, that will work. You can, I'm going to go back up to one. If you can change this structure, if you can lower this structure and make less of a drop, then there's less energy and there will be less of a recirculation, because you won't have the drop that provides the energy for the recirculation. The other thing that one of the other pieces you can do is controlling position of the horizontal transition. So this is one of the things we looked at quite a bit in the research. The ramp is exactly the same. The flow conditions are exactly the same. The only thing we did was change the position of the transition. from being really low to being really high, and we changed the position of the tailwater. And what we found was that if the transition was low, the tailwater was low, it made a wave. If the transition was high, tailwater was high, it made a wave. If the transition was low and the tailwater was high, then it made a recirculating hydraulic. So one of the ways that we know we can prevent these things from happening is if you move these transitions. The next part was the effect of the channel walls. We did a bunch of research on this too, particularly because of the kayak engagement part. With the full channel walls, you get a beautiful wave. If you take out one of the channel's walls, the wave starts breaking and the wave gets smaller because it's getting flooded in from the side and it's losing some of the energy that's being used to push back the tailwater. So if the wave starts breaking, you put in channel walls, then that to a point can help you keep your wave good, keep your wave as a high quality wave. This also is a way to allow a transition between a kayak wave and a surf wave. So if you lower the sidewalls, allowing kayakers to come in, it creates a bit more of a foam pile, which they like. So this is the concept that we're working on. We're doing the preliminary engineering on in our large wave project. So that is this one here. So we have tailwaters that increase from low flow conditions to high flow conditions by about 1.5 meters, I think it is. And the flows go from 50 CMS to the stage where we have to lower the structure is 300 CMS. And then the 1 in 100 year flood is 2,000 CMS. So during that operational range of like 50 to 300, we have a tailwater change of about 1.5 meters to 2 meters. Maybe that's a bit high. Let's say 1.5 meters. So based on what we've been looking at on a few other locations, what we just talked about, the concept that we're working on and currently in the preliminary engineering, going to be doing the modeling for it, is there's two main components of it. Let's say three. We have an adjustable gate at the top, which allows us to increase the drop during the low flow conditions, and also during really high flows, we can try to minimize the drop. We have a fixed transition at the bottom that's also protecting scour. We have this mattress of riprap downstream, which is holding the bed elevation. If we don't have this riprap downstream, the concern is that when the high flows come, it's going to dig out this riverbed and drop the tailwater and reduce the quality of the wave. So we have this tailwater control downstream. It doesn't move. There's no concrete. We're just putting riprap in the riverbed, and that's been quite effective. And then the last piece is this kicker here. These two kickers here, all they are is hinged. They have a very slight movement. They go from the down angle and they go to horizontal. So in the lowest flow conditions, we have everything down. The wave comes over the drop and it forms based off of the tailwater elevation above this pad. The next part that we're doing, water level increases a bit. We provide a bit more energy to it and use the second kicker. So the idea here is that we're keeping the distance between the tailwater and the height of this transition the same by turning on the kickers as the water level increases. And then the last one, the highest flow, we use the highest kicker. So the reason why we want to do this is because we think it's a really simple and elegant solution to managing wave safety and wave quality when you have big changes in tailwater. So an example of where a situation happened with the static wave and tailwater problems and how they effectively fixed it. So this just happened this spring and beginning of summer, and it was a really big issue. The wave was turned on. They had a not very good feature here. Oh, sorry, the Solita wave was built by Mike Harvey of Recreational Engineering and Planning. The wave is fantastic. It's really, really good wave. It was considered one of the best waves in the United States at the end of the summer for river surfing, best manufactured waves. The only issue it had was this tailwater management that I'll talk to you about. The wave gets used from the moment from dawn, the moment lights hits it until nighttime at like midnight. And there's a video cameras, there's a webcam of the wave. You can watch it all day long and see all these people surfing. The town has 4,000 people, and the economic impact just already from that summer was substantial because so many people coming here to surf. So they built a fully fixed structure, really beautiful, nice curves on the transitions, really smooth bottom, big 2-meter wide transition at the bottom of their slope. All of the designs for this are available online, or you can ask me. It was published in their council meetings. This is what it looked like before they did any modifications. The wave looks fine. Well, I mean, it looks really like it'd be really fun to surf. But they didn't have. This is just what we saw in that picture. So you've got this low sidewalls, not a big bank up here. It made a good wave, really fun to surf. The gentleman who designed it, Mike Harvey, owns a surf shop and lives right beside it. So he's living the dream that we all have of having a wave down the street that we can play on. This is what happened when the water levels went up. So the tailwater increased and it created this bigger circulating hydraulic. So this got tons of negative coverage immediately. Mike went down there and swam through that thing every day, many times to make sure that it was safe. No one got stuck, no one got hurt in there, but it did release you, but it looks really scary. And if the water level gets higher and higher, this can get worse and worse until eventually the whole thing gets can flatten out. So they needed to find a fix to change this wave from being recirculating hydraulic to a good wave. The difference in water level, this was at about 800 CFS, which is so this is about 22 cubic meters a second. It went up to about 24, and that was about the transition when it happened. And anything higher than that, it was from like 22 was where 22 cubic meters a second is where it was a wave. And then above that, it started turning into a hole and rapidly became quite scary looking. So how did they fix it? The result of it was they turned it from being, so this is the even higher flows. They turned it from being a scary looking recirculating whitewater into a huge and incredible wave. So you can see some of the things, the main things that they did were they blocked off they put bags at the top. You can see these huge sandbags, and they did this by crane. And they put this in at the higher flows. This directed more water into the wave channel, which is provides more energy for the wave, and it pushes back the tailwater. You're balancing out the energy of the water coming down with the force of the tailwater pushing back on it. So by forcing more water through the channel, they increased the drop from headwater to tailwater, and that helped push the wave back. And the other thing they did is they put in channel walls using sandbags, and this stopped the water from recirculating from the side, helping the wave collapse and helping reduce the impact of the energy of the water from downstream. And the result was, this was from the rest of the summer, where they had kids on it, they had tons of crowds, lots of people surfing, beautiful wave for the rest of the summer. And this will be all of you, which I'm very jealous about, in 30 minutes or so, I imagine, or maybe less. So that's it. That's the idea behind simple waves and safe tailwater management. An example of talking about the key parts of making a wave and what you need to do in order to allow a wave to work over a wide range of tailwaters. And lastly, the example of what happened in Salida and how they managed it. And that's it. Thank you very much.
Thanks for the presentation and for waking up so early. I think does some of you have a question to Neil?
Yeah, I was.
Please, Maurice.
Yeah. I don't know if you can hear me. I'm just.
Yeah, good point. The mic. Thanks for reminding.
So on the wave that you showed with the adjustable kicker, do you foresee any problems with gravel getting under the kicker?
No, good question. No, because these ones are on a slope. So here, this has been done. We did something like this with just one kicker, so there was no tailwater control on it in Bend, and that's been operating since 2016, and there's been no issues with gravel getting caught under there. There will be issues with sediment underneath here, very likely, and the idea is to do an inspection once a year, use the other parts to divert it, and use the others because this is a few sections wide. So when we do the inspections once a year, the idea is to be able to direct the water flow away from where we want to inspect. We're not trying to dewater, so the water will still be there, it just will be moving very, very slowly. Then you can go in and inspect it with divers in order to make sure everything's going okay. Boise does that on an annual basis. Bend does that pretty frequently. And it costs, I think their operational costs on those are a few thousand, maybe definitely under 20,000, maybe under 10,000 a year. So short answer, no, I don't see an issue. If there is any sedimentation buildup, then you remove it during inspections.
Next question. I was just wondering, you as a company, what kind of you're providing design and consultancy, or is this a non-profit?
It's a company, but it's a company. I was doing it full time, but it wasn't enough to make it. Wasn't enough to do it as my sole source of income, because it's kind of niche. So what we do is we work with we'll consult with the engineers on the projects. So for the design part of it, we'll work with engineering firms who will do the actual engineering, and then we provide them with the information they need in order to build in order to do good engineering design for the waves. The issue is waves are they're not hard to build. Like the concepts are very simple. Like any river project is really hard, but the engineering of river waves is not incredibly challenging. The problem is, any good river engineer around the world could engineer a river wave. The problem is the information is so niche, so it's very, very specific that most river engineers don't have any experience with it, and they don't know anything about it. So what we're trying to do is provide the information to make it easier for the engineers to design good waves, just make it easier for them to do their job and be successful. The other part of it is we also do work on like economic impacts and like the conditions required to build a wave and helping the communities progress their projects.
Great.
Thank you. Some more questions? We still have a little bit of time. Okay, there are not any. I think thank you a lot once again, Neil.
No problem.
Prague is greeting. So have a nice beginning of the day. Enjoy your breakfast and
well, thank you. Yeah, thank you very much. All this information is on our website. If you go to surfanywhere.ca/articles, there's a wave research section. There's information on the economic impacts. $60 billion a year industry. That's wave tourism. It's a $60 billion a year industry. So there's information there to help you sell your projects to your communities, and information there explaining how wave works. Thanks very much for your time, and have a lot of fun surfing. Good luck on your waves.
Bye-bye. Thank you, Leon.